I want to give you some brief explanation why these two formulas are so important in our real-world application. Here I use a simple example, image denoising. Image denoising application, right? Yeah. Here I only give you some, high-level, relatively simple explanation. Yeah. Later, I will talk about digital signal processing, so I will have more chance to expand, application like this. All right. In image denoising, so you have the normal image content mixed with the noise part. Yeah. The hard part is it's not very easy to separate the noise and normal image content. Yeah. All right. So there is a simple idea to separate, because you need to find a convenient way to separate image content from the noise part. All right, how to separate? Yeah. All right. So here we treat image as a function. Yeah. Image as a function. Yeah. How to treat image as a function? Later, when I talk about digital signals, I will expand this concept. Yeah. Here I want to save some time, so I cannot spend too much time. Excuse me. All right. Yeah. So here you assume we have a function representing the image. All right, content. All right. Then the original f function. Remember, we're working for some of the application. We work in the time domain. But for some of the application, we work on the spatial domain. So image, we work in a spatial domain because x, y coordinate. Image, so we have a rectangle size image. So we have x coordinate and y coordinates. Yeah. So we call it spatial domain. Right. Yeah. So when the noise inside image in a spatial domain, it's hard to separate. How to separate the noise from the image content. All right. Then we do Fourier transform. We apply Fourier transform on our image data. So then after the Fourier transform, we move to the frequency domain. So here, this is W. So we move to the frequency domain. Different domain. Okay. Then the image functions in different domains have different properties. In the frequency domain, then it is much easier to separate the noise part and the image content part. Much easier to separate, yeah. Because the noise part usually focus in the high frequency part, okay? Yeah. So the noise typically located in high frequency part of the image. Okay? Then we just want to remove the high frequency part, certain part of the high frequency, cut off. Okay? How do you cut off? Yeah. So in image, we remove that. We apply a high pass filter. high pass filter, digital filter, high pass filter. High frequency part, we pass it. Okay, yeah. We do not make that part of the information pass through the, processing result. Yeah. Low pass. Sorry. Yeah. We cut off the high frequency. We apply low pass filter because we want to the content relatively low. Pass. Okay. High frequency part, we do not let it pass. Okay. We block it. Low pass filter, high pass filter. Yeah. Yeah. Depends on application. So, low pass filter. Yeah. All right. Yeah. Yeah. Although there are many ways, so this is just one of the ways. Yeah. Yeah. Actually, it is very complicated. Yeah. So here I just give you a simple idea. Okay. So in the frequency domain, it's relatively easier to remove the noise. After we remove our noise, then we need to get back to the original spatial domain. So we apply Fourier transform on the, the part we processed in the frequency domain. We want to get back to the spatial domain. Yeah, so we apply inverse Fourier transform. We can get back to the, original. We try to recover original image, although there is some small amount of loss. Yeah. Because after you remove the noise, your image quality sometimes, could be, some places blur a little bit. Yeah. But if your software is better, yeah, so that's why people need to develop, many algorithms, try to do the denoising better. Yeah, a lot of algorithms. Yeah. All right. So that's the typical application. Yeah. All right. Yeah. Properties of Fourier transform. Yeah. Existence Fourier transform. Yeah. Here, this theorem, the condition is very simple. The first condition, f of x is absolutely integrable. Yeah. So last time I talked about this condition. You take absolute value, then you take integral on the whole axis. It is a finite number. The integral is a finite number, so we call it absolute integrable on the x-axis. And second condition, piecewise continuous on every finite interval. Yeah. Then the Fourier transform of that function exists. Yeah. All right. You can apply this Fourier transform formula. All right. Linearity, very simple. Yeah, pretty straightforward. Because integral operation has the linearity property, right? Yeah. It just inherits the linearity property from the integral operation. Yeah. All right. Fourier transform of derivative of x. Yeah. So you apply. Yeah. Remember. So you need this condition. Okay. Then partial integration by parts. So you can get this formula. Yeah. 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 Very easy. Yeah. All right. Yeah. 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 So here, double derivative, right? Yeah. So you have that. Yeah. All right. For a transform on convolution operation, yeah. So convolution operation, yeah. Another useful property we need to use for the Fourier transform. Yeah. Convolution, we did this in Laplace transform. Yeah. So we know the definition of convolution. Yeah. And in Laplace transform, yeah, we have this property. Yeah. Fourier transform, we have a similar property, slightly different from this one. Yeah. But the difference mainly at the coefficient. There is a coefficient, yeah, special coefficient. Yeah. Yeah, here you can see for the convolution operation, yeah, Laplace transform, there is no special coefficient. Yeah. It's 1. Yeah. So it's perfect. Yeah. For Fourier transform, yeah, there is some extra coefficient. Yeah. Yeah. Not that perfect. Yeah, but it's not too bad. Yeah, it's not too bad. Yeah. All right. Yeah. Sometimes we need to use this convolution theorem to help us calculate the Fourier transform, yeah, or inverse Fourier transform. Yeah. All right. Yeah. Yeah. So, another formula. Yeah. This version, you can see there is no extra non-trivial leading coefficient. Okay, yeah, no such special coefficient. Yeah, so this version looks, perfect. Yeah. All right. Oh, yeah. Sorry, I finished part A. Yeah, now I can go to part B. Yeah, all right. All right. Part B, actually, the first topic of part B, so that's the convolution thing. Yeah, we can skip. Yeah, all right. So here, the title, discrete Fourier transform, part B. Yeah, convolution, we just did it, so we can skip this. Yeah, because let's start from this topic. We want to talk about discrete Fourier transform. Yeah. All right. Let me give you a short introduction on the discrete Fourier transform. Yeah. Why we need to consider the discrete version? The previous one, it's the continuous version. So now we need to look at the discrete version of the Fourier transform. Why it's important. Yeah. So I need to give you some background information. All right. From analog to discrete. All right. Yeah. Yeah. So here, let's look at our data, the form of our data. Okay. Yeah. When we work on our data, so you need to consider what's the original form of our data. Yeah. So that's important. Yeah. So let's consider original form of data. Okay? Yeah. Currently, all of our formulas are developed based on functions, right? Yeah, based on functions. Yeah. The function is very close to continuous function, although we allow discontinuity. Yeah, but the discontinuity we assume the discontinuity not too bad. If the discontinuity is very bad, so then we cannot handle. Okay, yeah. So typically we consider a continuous function we start with limited discontinuities. Okay, yeah, the continuity cannot be too bad. Okay, yeah, yeah, all right, yeah. The limited, yeah, so we want to put some conditions on the discontinuities. Okay, all right. Yeah, so let's recall our conditions on the discontinuities a little bit. Yeah, all right. For the Fourier series, yeah, let's go to the Fourier series. Yeah. In order to make the Fourier series convergent, yeah, we have some condition on the discontinuities, right? The left limit, right limit must exist, right? That's the condition we need on our discontinuities. Yeah, left limit, right limit, both exist. Then our Fourier series convergent at that particular discontinuity point. Yeah, that's the first special case. So we put a conditions on discontinuity. Second one, yeah. So our Fourier transform, we just learned existence theorem for the Fourier transform. Yeah. Other than the first condition, absolutely integrable, that's the first condition. The second condition related to the discontinuities, right? Yeah. So the discontinuity, when you consider any finite interval of the function, the number of discontinuities must be finite. That's another condition related to the discontinuities. Yeah. So under these two conditions, then we can work on the, Fourier transform, Fourier series expansion, yeah, and so on. Yeah. All right. Yeah. So that's the originated as a continuous function. But in the real world situation, think about our real world situation. Typically, our data is not as a continuous function. How can you think about how do people acquire the data in the real world situation? Think about that typical process. Okay? Yeah? All right? Yeah? Image file, sound file, video file, satellite data, geographical, geospatial data, all those data. What's the form of the data? Think about that. Medical imaging, what's the form of the data? Okay? Yeah. Digital data. Data is in the form of digits, numbers. Yeah. So our typical data is in a form, because right now we do our application in the digital world, right? Yeah. So we are living in a digital world. Okay. So our data, most of our data in the form of the digital data. Okay. Yeah. So we consider the form of the data. Typically, it's digital data. Digital data, you have a sequence of numbers. That's your data. So you are not given a function. You are given a sequence of numbers. That's the original data. So data is a sequence of numbers. Okay? So you will not get a continuous function. Okay? So basically you get a sequence of numbers. Like a sound file, music file. It's a sequence of numbers. Okay? Yeah. So if you can view the content, yeah. So if you apply some special software, you can view the content. It's a sequence of numbers. Image also, pixel values, right? Yeah. Each pixel there is RGB values. Okay? RGB value. Red, green, blue components. Yeah. Color, 3 color components. Possibly the fourth one, transparency. Yeah. If you have the fourth component. Yeah. All the digital values. Okay. Yeah. Images, videos, all in digital format. All right. Yeah. So you need to get a digital version. Your data processing tools, the digital version is more useful. We are working on digital signals, digital data. Yeah. So we need to, yeah. In the digital world, we should use the discrete version of the Fourier. When we apply Fourier transform, we cannot use the continuous version of the Fourier transform because we do not have a continuous function. So we should get a discrete version of the Fourier transform. More useful in the real world applications. Okay? Yeah. All right. So with this, now we need to think about how do we make the change. We go from analog version to digital version to discrete version. Yeah. Discrete, digital, same thing. Yeah. All right. Sequence of equally spaced, yeah. So equally spaced, sampled data points. Yeah. Look, yeah. Here I use sound file and image file as two examples. Sound file, the signals given based on the time, right? Yeah. So you need to take equally spaced sampled on time axis. Yeah. So yeah, equally sampled. Yeah. So there the value higher, lower, the pitch, higher, lower. Yeah. So that value. So you get that sequence numbers. Yeah. Then for image file also you sample the x axis, y axis, the box, the corresponding to the size of image, equally space sampled. Yeah. All right. Horizontally, vertically, equally space sampled. Yeah. So each pixel you have RGB value. Yeah. So that's your data. Yeah. All right. Here, yeah. For simplicity, here we consider a sequence of data points. Yeah. So here we do not want to, do the two-dimensional data, right? Here we can imagine we're working on one-dimensional data. Yeah. F is a 2-pi periodic function. Yeah. Yeah. All right. Yeah. 2-pi periodic function. Yeah, because although many functions may not be 2-pi periodic, but if the range is limited in an interval, we can consider 2-pi periodic extension, right? Yeah. So for our sound file, the values is in certain range, right? Yeah, certain range. Then we do the 2-pi periodic extension on that range. Okay. Image file, RGB has a range of the value, right? Between 0 and 225 for each component. RGB value, each component, 0 and 255. Yeah. 1 byte, right? Yeah. 1 byte, 8 bits. Yeah. We use 1 byte, 8 bits to represent one component of RGB. Yeah. There is a certain range of the value. Yeah. That means we can treat as a 2-pi periodic because we can do 2-pi periodic extension of this range, right? Yeah. So that's no problem. No problem. Yeah. Yeah. So it's not very too much limitation. Yeah. For this 2-pi periodic, not too much limitation. Yeah. For typical real-world applications. Yeah. Not all. Definitely not all. Yeah. Yeah. All right. Then, yeah. Each sample locations, yeah, xk, that's the sample locations. Okay, equally spaced. See, 2 pi k over capital N. Yeah, k. Yeah, the subscripts k. Yeah, takes these consecutive integers. Yeah, the sample location. So that's our data. So now we need to work on the typical data like this. All right. Question: how to approximate function f of x with a convenient function? Yeah. Yes. So here, actually, another understanding. Yeah. So in this short introduction, I need to give you a lot of background information. Otherwise, you may feel not comfortable when you work on our special operations. You may not feel comfortable. All right. Here, the question, this little f function, what is this little f function? Look at that. Okay? What is that little f function? We are given a sequence of data points. So a better way to write, here I use this little f function, but you may ask, what is that f function? It's hard to answer, right? Because it does not exist, right? The f function does not exist. You use that function, but nobody tells you what that little f function is. Nobody knows that. Yeah. So a better way to write this sequence of points should be xk comma yk. You only have the yk value. You don't have that little f function. Yeah. So you have the, coordinates, x location, yeah, x coordinate, y coordinate, yeah, function value. You have function value, but you do not have function. So you have the sampled function values, sampled, but the original function nobody knows. What's that original little f function? Nobody knows that. You just have a sequence of data points. Sequence. Okay? All right? Yeah. Like the stock, a sequence of data points. Stock data, right? Temperature data, right? Temperature data. Yeah. So a lot of data, a sequence of data points. But there is no specific function. Okay? All right. Yeah. So then, now, but sometimes people also refer to some little f function. People refer to that, it's an imaginary function. In people's mind, there is an imaginary function. Yeah. But in the real world, it does not exist. Yeah. In our thinking, sometimes we like to use some imaginary function. In our thinking, yeah, because when we do math, we like to work on functions, right? Yeah. So when needed, we use imaginary function. Yeah. But imaginary function, you do not have the concrete form, specific concrete form, But sometimes you need to apply math tools on the function. Yeah, you take integral, derivative. If you have imaginary function, how can you apply math tools, mathematical tools on imaginary function, right? You have to have certain concrete function, then you can work on. In that situation, we need to do the modeling of our data. Modeling. Yeah. Because no specific function, but people really need to use that function, then people need to do a step, mathematical step. That's the modeling. Modeling step. Modeling step, you construct an appropriate function passing through all the data points. That appropriate function, you construct it. Okay? Yeah. You build it. You build it. You construct it. Yeah. So now, that's the modeling step. We model the data, the given data. There is no model for the given data, but we need to build a model for our given data. Okay? That's the modeling step. Yeah, that step also important. Yeah? Because many softwares, many important tools, if you do not have functions, you cannot apply those tools, software. You cannot. Okay? So in that situation, you need to build that step, construct a modeling function passing through. So that's another topic. It's not in the scope of this class. In this class, we do not have time to talk about modeling that part. That's important. Yeah. Unfortunately, we don't have that much time to do it. All right. Yeah. Yeah. All right. Convenient function will approximate the function. Yeah? So in this way, because in our discussion, we need to frequently use this function concept. Yeah. Okay? Yeah. So here, before we find any problems, I want to give you some environment description. Yeah. All right. Use a complex trigonometric polynomials. Yeah. 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 So this time, complex trigonometric polynomial. It's not a trigonometric polynomial. We used trigonometric polynomial before, right, for approximation. Yeah. So we have cosine terms, sine terms. Now we combine cosine terms, sine terms in one e-function term. One e-function term. So that's the complex trigonometric polynomial. What's that? The Q function polynomial equals summation, coefficient, Cn coefficient, then e to the I n times nx. Yeah. That's the complex trigonometric. Inside e function, you have cosine, you have sine. Yeah. So we can still call it trigonometric polynomials, but the complex version of trigonometric polynomials. Yeah. All right. So we use, here you can think we treat it as a modeling function, right? Yeah. Because there is no original function. Yeah. Now, how do we model the data function? How do we model the data function? We use complex trigonometric polynomial, this version, to model the data function. Okay? Yeah. When we do the data modeling in this form, yeah, so this is a special form of the data modeling. What conditions our modeling function should satisfy? F function, yeah. Yeah. We want to make our f function take this special form. Okay? That's the modeling, the meaning of modeling step. We want, so this Q function, but think about it. We want to make our f function equal to this function approximately. Yeah? Because we cannot guarantee it's a perfect fit, right? It's not perfect. Yeah. It's approximation, close. So this Q function is close to our original f function. Definitely there must be some certain error. Yeah. So we don't know how large is the error. We just hope we have some approximation in this form. Yeah. Now you consider, in order to get approximation, there must be some conditions our modeling function should satisfy, right? Yeah. Think about what is the natural condition for our modeling function. Natural condition. These points should, our given data points should fit into the modeling function, right? Think about it. Our modeling function should pass through all the data points, right? Is it natural? Passing through all the data points. Otherwise, it's not a good modeling function, right? Yeah. So the bottom line is our modeling function should pass through all the given data points. That's the bottom line. Otherwise, it's not a suitable modeling function. Okay? Yeah. Passing through, that means when you plug in, okay, the x part, when you plug in xk, little xk, in this complex trigonometric polynomial, you should get yk, right? You should get a yk. Yeah. Yeah. Sometimes people may not use yk, people use little fk. Yeah. The same thing. Yeah. Because people want to connect to f function. Yeah. So just write the yk as fk. Yeah. Fk. Okay. Yeah. Yeah. All right. Interpolation. Remember, I used this interpolation concept before, right? Yeah. Here we use it in another place. Interpolation condition. Yeah. I talked about linear interpolation concept before. Yeah. Here we do the data interpolation. Data interpolation. Simple fk. Yeah. It's meaning that imaginary little f function of x sub k, yeah, you plug into the Q trigonometric polynomial, yeah, you plug in. Yeah. That's the interpolation condition. Yeah. So our modeling function should satisfy the basic interpolation condition. Yeah. Then we can accept this modeling function. Okay? Yeah. We can accept. So now we have a function. Yeah. Right? Yeah. So now we have a function. We can apply mathematical tools on this modeling function. Okay? Yeah. Now it's not imaginary. Now it is concrete. Okay? Yeah. All right. Now let us work on this trigonometric, complex trigonometric special form. Okay? Yeah. All right. All right. The next question, we need to determine the coefficients, right? Yeah. Yeah. Given, yeah. So, yeah. Other than the xk locations, yeah, equally spaced location, that little f xk. Now, the function values, little fk function values also given. The question, how do we find little c coefficients? Little c coefficients from little f values. Yeah. So the first thing, we need to calculate this little c coefficients. After we find little c coefficients, then we get a modeling function. We find the modeling function. Yeah. formula for discrete Fourier coefficients. Those little c coefficients we call the discrete Fourier coefficients. Discrete version, yeah, all right. Fourier coefficients, yeah. Yeah. For the name. Yeah. All right, yeah. So we start from this formula, okay, all right. Now we consider calculation. We need to solve linear system. Is it a linear system? So we get a linear system. Okay? Yeah. Matrix. So we can use the, yeah, so here. Yeah. Oh, the thing is, the formula can be found. Okay? The formula can be found. Yeah. Yeah. Later we can prove. Yeah. So now, here I write the formula. The way to calculate the formula in this way, like a Fourier transform, right? Yeah. But this is the discrete version of the Fourier transform. You can compare with the continuous version, but this is the discrete version of the Fourier transform. Yeah. All right. Discrete Fourier transform. Yeah. All right. Yeah. Discrete Fourier transform, this f, capital N times little c, cn, capital N, yeah, because we need to get rid of this 1 over n, okay, yeah, equals this summation, okay, yeah, we can calculate. So we call it discrete Fourier transform. Yeah. Why is that? Later we do comparison with the continuous version Fourier transform. Let's look at, what's the difference. Here, I just give you the form. Then, the given data, we use a vector to represent the given data. F vector, little f vector. The given signal or data, yeah, sometimes people call it signal, but the signal is a general signal. Okay? So our understanding, the digital signal, any data we can call signal. Yeah. We generalize the concept of signal. For example, the stock data we can call signal, general signal. Okay, temperature data we can call signal, general signal. Okay, yeah, yeah. So for the word, so we want to make it general. Yeah, yeah. All right. Yeah. So the input data, this is input data. So it's a vector. Yeah, we use vector to organize, to represent our input data. Sequence is a finite sequence, so we can use a vector to represent it. Finite sequence. Yeah. All right. Then, Fourier, discrete Fourier transform. We still use the hash symbol. Yeah, capital, boldface vector. Yeah. So it's another vector with the same dimension, capital N dimension, dimensional vector, original signal. Then the frequency part, yeah. So the Fourier transform. So you go to the frequency domain. Yeah. In our frequency domain, we use another vector, same dimension. Okay, capital N dimension, vector. Yeah, but coefficients we calculate in this formula. Yeah. All right. Yeah. Frequency spectrum. Yeah, we call it the frequency spectrum. Yeah. Spectrum, yeah, the spectrum containing the frequency values of the full range, right? Yeah. So low frequency, high frequency, yeah. Frequency. Yeah. Look at this little n. Yeah. How do you understand frequency? The n from 0, 1, 2, 3, from low to high, right? The n number. The lowest little n is okay. Yeah. Okay. This little n. Yeah. N here, right? Yeah. Remember n, that n. N also from, look at n also from 0 through capital N minus 1, right? The n value. Okay? N value. Yeah. Yeah. All right. Frequency spectrum, covering the information of all the possible frequencies. All right. That notation, now we need to use matrix notation. Little w, because this special e, that e function, this one, so we need a special notation for this special e representation. Then all other e representation can be the power of this w, right? Yeah, the power of this w. So discrete Fourier transform, we can use the matrix version, okay? But there is this capital F sub n matrix. We use the w to certain power, n x, row number, column number, big matrix. Capital N by n, big matrix. So organize rows, columns using that little w element. The w is as one element. Then all the other entries can be represented, the power of that little w, the basic element. Okay? Yeah. So the structure, this capital F matrix structure is very special. And very convenient to use because later we need inverse matrix of this one. The inverse matrix is very easy to find. Inverse matrix. So for the inverse Fourier transform, we need to take inverse. So this is a Fourier transform. For the Fourier transform, we multiply this matrix. For inverse Fourier transform, we multiply inverse matrix, right? Fortunately, its inverse is very easy to calculate. It's inverse. All right. So let's do the remaining part next time. All the discrete version Fourier transform.